Hi everyone, I am Dario Caramelli
And I'm Hessam Mehr.
from the Cronin Group at the University of Glasgow, and I'm here to talk about our use of probabilistic methods in the chemical discovery. So, one of the main goals of the Cronin Group in the last few years was to digitize chemistry. In other words, to bring the chemistry knowledge and the literature procedure in silico, and ideally to have a platform capable of taking a bunch of code, so a list of operations, and output and perform the synthesis of the molecule and output the final product, also in a multi-step way. So this is the platform, and it's called the computer, and it is designed to reproduce literature's procedure. So it has a series of pump and valves to mix a set of reagents into a reactor, and there is an evaporator to remove solvent and a filter to crystallize the final products. And this has been used already for multi-step synthesis and successfully. The project that I'm actually talking about today is a spin-off project from the computer, and in our case, instead of reproducing literature procedures to achieve known molecules, we want to use a platform to discover unknown reactivity, so new molecules and new reactions. In order to do this, we use a closed loop approach. So we have a liquid-handy platform, so a way to perform these reactions practically. Then we have an automatic analysis equipment. So we have 3 different instruments to acquire 3 set of spectra from a reaction. We have an NMR, an HPLC, and a mass spec. Then we design a data processing algorithm to automatically process this data and assign their activity value to reactions. In other words, this is an assessment of how interesting is the reaction, if something interesting happened or not. Then this reactivity value, in our case, is simply 0 or 1, so it is reactive or not. Then the reactivity value is correlated back using a Bayesian model to the reagent used, and hopefully through the Bayesian model we can suggest new combinations to the platform to perform. And through this closed loop approach, basically we are exploring the chemical space, so all the possible combination of reagents in a smart way, driving the platform with the model and the analysis to perform the interesting reactions first, basically. Beginning with the hardware, so this is our platform, what we build. We have a set of pumps and valves to mix up to 25 reagents into 20 parallel reactors. And after 24 hours, the reactions are pumped into the 3 instruments, and the data is automatically acquired. This platform is part of the computer family, so the code is also interchangeable with the rest of our platforms in the group. This is the chemical space that we chose. There is nothing really specific about these particular molecules. We just tried to design the chemical space to have the large variety of functional groups and to have molecules that might have an unpredictable behavior with each other. Then we wrote the algorithm to assess their activity. In all cases, we are comparing the data of the starting materials alone with the data of the reactions, and basically if we only see signals of the starting materials, that we know that the reaction is unreactive. On the other case, if we see new peaks, then we assign a positive reactivity. So for the NMR, this was done with the convolutional neural network that compares the mixture of the NMR of the mixture with the sum of the starting materials. For the HPLC, this wasn't necessary, so we're simply looking at the peaks, since each peak corresponds to a series for a different product. And if we see new peaks, then the reaction is considered reactive. And same thing for the mass spec. All the 3 assessments are combined into a reactivity assessment. And just to show the path, so we are here. So in the last step to close the loop is the Bayesian model. So we need to find a way to correlate these observations to the starting materials that we use and infer reactivity of reactions that we haven't performed yet. Basically, if you think about it for a second, this is what we're doing. So we have two entities or two or more entities reacting with each other, and we have the observations that the reactions that we did already as observation, and we're trying to predict the chances of the possibility of the unperformed reactions. In this case, with only two reactions and three reagents, it's kind of hard to tell. But imagine that the more reactions that we perform, so we have more reagents interacting with each other, hopefully we will build a network of reactivity of the molecules with each other, and our predictions will become more and more accurate. So how do we do this?
Yes, so I remember first discussing this with Dario, and it seemed like quite a difficult problem. So we decided to take a step back from the chemistry that we learned in school and in our degrees, and just go back to the sort of historical origins of chemistry. And what seems really intuitive is this theory that compounds have properties, and what we see, the reactions and the behaviors that we see are manifestations of those properties. So going back to the days of alchemy, there have been these sort of basic elements of air, earth, water, and ether and fire, and each of these was described as having certain tendencies towards the others. And so thinking of our current understanding of chemistry, it's not really fundamentally different in that it's still a model. It's just a tool for us to understand and to predict things. So we decided to take on this simple model of chemistry, essentially coming up with a plan where we do a whole bunch of different combinations, and you can see in this figure, so some of them lead to reactions, the red dots, and then some of them just don't do anything. And based on those observations, infer some abstract properties that exist, and then relate those properties to the presence or absence of certain structural motifs. And this third step is for the benefit of the chemist, because then it allows us to communicate the novel findings, potential novel findings, to chemists who will be able to take and use them in their work. So in the simplest version, the model basically works as follows. So each compound has the possibility of having a number of properties to a certain extent. So these two vectors, P1 and P2, are the property vectors for these two compounds. And higher numbers mean that this compound has more of that property. Now, if you basically do an outer product of these, you get the probability of them simultaneously having these properties. So in this case, for instance, there's a high probability that compound 1 has property 2 and compound 2 has property 4. And then we imagine for each pair of properties the mutual reactivity of those properties. So this is a matrix that we ended up having to constrain, where the diagonal has 0 reactivity in the final version of the model. But essentially it's a symmetric matrix. So property 2 and property 4 have 0.67 probability of reactivity. And so you can then put all of these together and find out what the final probability of observing any sort of reactivity is, and check that against the observation. So use the observation to essentially condition all of these, so the P1, P2, and R matrix. So far, what we've assumed is that these compounds are black boxes. So if you just think of a compound as a vector of 4 numbers, then it's not very useful for the chemist, because then they're like, okay, if I put a new compound in there, what do we know about it? And in that case, we know nothing. So we were hoping to find a system where we can carry forward any sort of knowledge that we acquire about a compound to compounds with similar structures or similar structural motifs. So what we used in the end was a fingerprint model, where essentially for each sort of collection of atoms in this structure, you have a hashing algorithm that assigns it to a certain position in a bit array. Right? So then each compound can be represented not losslessly, but in a lossy representation as a collection of ones and zeros in a fixed length bit array. Now, if we then, instead of saying compounds have properties, say fingerprints or those motifs have properties, then we can, for each compound, find out which ones of the bits are turned on. So in this case, for this particular compound, toluene sulfonic acid, you see that we have a number of turned on bits. And for each of those, you have the properties. And then you have to decide how to aggregate these to get the final properties for this compound. And what we used was the simplest possible reduction, which is to take the maximum. But you can imagine much more detailed models where there could be sort of antagonistic interactions between properties, for instance. So here we see a little test of this kind of model where we're trying to discover a Diels-Alder reaction. So this is a reaction where a compound with two double bonds, so these double bonds in this cyclic compound, reacts with another compound that also has a double bond, the carbon-carbon double bond. And so proposing to the program the following observations, so that this cyclic compound only reacts with itself and not with any of the other compounds, but that these compounds have properties towards each other, gives the model a chance to come up with the simplest possible explanation. So in this case, because the model that we use takes advantage of a stick breaking process, which is naturally conservative in allocating properties, it ends up using the least sort of required allocations of properties. So this is a typical sample from the chain, and we can see that compounds 4 and 5, so these two have a certain property, and compounds 6 and 8 property 0. And we can see that properties 1 and 0 are reactive towards each other as expected, so to justify these two positive observations. But then compound 0, interestingly, has two properties, and that comes because we specified that properties are not reactive towards each other, and that really lines up with the chemist explanation of this reaction as occurring between what is called a diene, which is the compound with the two double bonds, and a dienophile, and that's a compound that reacts with the diene. So that's a really sort of relatable explanation of the Diels-Alder reaction. So beyond these, beyond just explaining things that we've observed, we can use this model to explore chemical space, to ask questions about, okay, what compounds do I mix together next? What experiment do I carry out next? And so you can go and interrogate the innards of the model to come up with really interesting questions. What a lot of these automated platforms concentrated on, including our own work, was what is likely to react. So we're just looking for new reactions or things that are reactive, hoping that we'll find something interesting. But a lot of time these reactive combinations could be quite boring. So a sort of higher level, the sort of more interesting question is, which combinations are we uncertain about? Because answering those will give us more information, right? So if you know something's reactive, then if you do the reaction and find out that it is indeed reactive, you don't find out much. But when you're uncertain about something, definitely doing the experiment will uncover things. Or you can even go further and say which one of these potential reactions, if we tried it, would change our expectations about the other untried reactions or other mysterious reactions. Or even further and say which one of these is most likely to challenge my model or to stretch the model to its limits. So these are things that we like to ask, and we've found ways to kind of go and investigate and interrogate the chain to find answers to these questions. Now, it's not all sunshine and rainbows. There are issues with, there are limitations with this approach. And so we've had a few growing pains. The main thing being performance. So typically when we have many observations, and these could be thousands, we end up spending a good couple of hours sampling with PyMC3. And this was something that was not an issue with the smaller models that we use kind of to develop the methodology. But as we use the platform, which can perform thousands of reactions, it does become a bottleneck. So recently I invested the time to port the model to this newer non-pyro library, which uses Jackson, is capable of exploiting the GPU, and now it's about 5 times faster, which is sort of in line with what I saw on Twitter the other day of the PyMC3 people doing the same thing. So essentially getting around that sort of speed up. And that's good, but the problem is that then you need another GPU if you want to run another experiment in parallel. So something that can still be improved. The other major problem that is fairly specific to our use case, or not a general PyMC or MCMC issue, was that our problem had a really large degree of symmetry. Because these properties are by definition abstract, the actual numbers are completely arbitrary. So you can rearrange these and a very large number of permutations. So compound 1 can have property 2, compound 2 can have property 1, or vice versa, and it would be exactly the same. And this causes the sort of infamous label switching problem, where the properties become meaningless by themselves, and you have to find sort of surrogate quantities that will help you find meaning in the chain. Which was an interesting exercise, actually. It led us to think about things in a different way. But some of the more challenging problems are that these, because of the symmetry and because there are so many possibilities, you have very multimodal distribution. So either then you want the chain to explore all the modes, which is practically impossible, or to confine the chain to exploring one mode really well. But then you get potentially, because different chains can converge to different modes, you get all these large R hats, and it might seem like your chain is not converging. Or there could be multiple modes, but some of them might be better than others, but we'd never tend to explore those. So that's one of the things that I would like to learn how to, if it is something that can be addressed, to learn how to deal with. At the end, I would like to thank everyone who I've had the pleasure of working with in the Cronin group. We are a large group, so about 60 people, and come from all sorts of backgrounds, and it's really a pleasure to have colleagues of such diverse expertise. And also I would like to thank you, of course, for your attention. If this sort of line of research is something that you find interesting, definitely hit us up. We are hiring, so we'd love to hear from you. Thank you again. Thank you very much.